unweighted.
Hey, think about it. So I got a 75 on it.
Maybe that's not how weighted works.
5% curve.
Wait, isn't the weighted only count for GPA, not for letter grade?
No, well, it's the same thing.
I know, but
But at the end of the day,
and I know, but when colleges look at it, so it's still, my letter grade would still be a B plus instead of A minus. The GPA would be affected, would be weighted.
Really?
Yeah.
I'm pretty
Your
sure.
letter grade GPA.
yeah, it doesn't go on your transcript as an A.
No, it
But
goes,
your GPA.
Because what would they do if you got an A?
But they would.
What letter would they put?
You could just put like a star next to
and
it.
A plus plus, like Spanish 3 is get B plus plus.
Yeah, I mean, I like
Anyone
A
can
plus
get an
and
A plus
Spanish,
plus
That's
in
literally
Spanish.
like what's
I don't
happening.
take Spanish, so I can't.
Ask me anything in Spanish. I know no Spanish.
Hey, but think about it. I got
A
75 on
plus.
this.
Shoes.
Curved at 5%. So
I know.
I'm 80. And I get a 90 weighted. That's pretty good.
80 in college chemistry as a junior? Pretty good.
I'd take this class next year if I didn't have to take
Butter.
classes.
Like 8 classes next year?
Yeah, because I haven't done speech yet, and then I'm going to take physics,
Yeah.
Spanish 4, Bible,
Quiero
English.
que.
Tranquilo.
I don't know.
I'm not a
Fun.
senior who has
I like that.
What'd you say?
I've gotten to the point where when seniors struggle, I'm happy. Because I like the justice in it.
Because we're not trying? Or what?
Most of the time. Not all of you. Not all of you. But yeah. Like, when a senior doesn't try and they do bad, I like the justice in that.
Well, I mean, I got to take those weighted
I'm a junior, I tried really hard,
I
and
tried.
still did
I'm
bad.
not saying that's you guys. But,
Okay, so
I'm number
this
10.
class
In general.
And I know there's like 4.
Alright.
It's just a
Really
really
easy.
easy at that point. It's like there's so much to do.
I did like
11.
No, Britain's 11 to 10.
Oh, I'm 8. I was only
Like what?
8.
I'm like 8.
Like,
Okay.
well, we have theoretical like open house and like graduation. and
I don't
like,
need time. There's no way.
you have to get ready for open house?
I should be like,
Yeah.
What are you doing
I have
for
a
open house?
4.1.
like the cards. and
yeah, I don't need one either.
It's out of 4.33, so
Like
it's out
the
of
tests and
4.1.
stuff.
Oh, you're talking about senior, you're talking about graduation open house.
Yeah.
I'm talking about like open house
Well,
here.
they're still smart.
I was like, what do you have to do for open house here?
They all take classes.
Alright. So, we're moving on to chapter 16. This is talking about solubility equilibrium. So, we're still doing equilibrium. We're still going to do equilibrium expressions. But now we're going to do it for dissolving things. Okay? Specifically dissolving salts. As you guys have probably heard me say before, most of chemistry that's done in the natural world happens in an aqueous solution. What does aqueous solution mean?
Dissolved in water.
Salt and water. Okay? We will consider the solubility of salts in this chapter. We will discuss the equilibrium of dissolving and precipitating. What is precipitating?
Solid falling
A solid coming out of solution.
Yeah.
I mean, it's the same. You didn't say it wrong. Just said it different. A solid coming out of solution is called a precipitate. So there is an equilibrium between the dissolving process and the precipitating process. And so even though we don't see anything more dissolving and we don't see anything precipitating, they're vigorously going back and forth at equilibrium, because at equilibrium, what is true?
Equal rates.
Equal rates. So the rate of the dissolving process is equal to the rate of the precipitating process. Yep. Okay. All right. Solubility product, KSP. So now we had Ka, we had Kb, we had just regular K, we had Kp, now we got KSP. KSP refers to the solubility product, and let me kind of show you why we call it KSP. So if we have CaF2 as a solid ionic salt, we know that that's going to what? Okay, will completely dissociate. Why will it completely dissociate?
It's ionic.
Because it's ionic. And so the reason why we call it KSP is because this is a solid. So when we put that in the equilibrium expression? So it's really solubility products. That's what the KSP is trying to allude to. So when we are doing the equilibrium expressions of dissolving a salt, you will never have a product, or sorry, you'll never have a solid reactant in there. So if I were writing the KSP expression of this, KSP equals concentration of calcium 2 plus, concentration of F minus raised to the power of 2, and not over anything else. Okay, do you guys remember why solids aren't put in the equilibrium expression? Like what the reason for it is?
Change the concentration.
Cannot change the concentration because you cannot change the volume of, well, yeah, basically the density and volume of your solid. Now, I don't know if you guys remember some things that we can do to make things dissolve better. Does anybody remember some of the things that we could change to make something dissolve better?
Heating it up.
Heating it up would do it. Usually, not for gases, but
Right. Stirring.
stirring.
Increase atmosphere.
That would keep something dissolved. That would keep like a gas dissolved, just staying in solution better. There's one other
Add
one.
more salt in.
Sure, and more solvent. Well, that yeah.
It wouldn't.
But it wouldn't change the per volume.
No, it wouldn't. It would
Yeah.
just get more-
The last one is surface area. Do you guys remember?
right.
You increase the surface area, you've got more area of contact. Okay. Yeah, like you'd want to have crushed sugar versus a cube of sugar. Okay. Now I want to make something very clear. Stirring it, increasing the temperature, and changing the surface area makes things dissolve faster, but it does not change your equilibrium constant. Everybody understand what I just said?
Yes.
Okay, it makes the things dissolve faster, it makes them reach equilibrium quicker, but does it change the equilibrium constant? No. You can only dissolve a certain amount of a particular substance in a certain volume. You cannot change that by stirring it, by heating it up, by you name it. Okay? So still, the KSP, we will always have one value for KSP per given temperature. Here's another thing that you might think is possible. Usually there were some things we could do to shift equilibrium. Can you guys remember a few things that we could do to shift equilibrium?
Removing products.
Removing products,
Right.
adding reactants would cause it to shift. Adding or removing anything would cause it to shift, right? Okay. In solutions, adding more reactants does not shift it right. Right? So if I give you an example. If I put a bunch of salt in water and I dissolve it so that I can't dissolve anymore, would adding more salt cause it to dissolve more at that point? No, because there's only so much that water can surround particles. So we would normally think in a typical chemical reaction, adding a reactant shifts it where? Right. But adding more salt to a solution that's already saturated will not shift it right. Okay? Because there's no more room for the salt to even get into solution. Okay? So a couple things that you need to be aware of. We can make it reach equilibrium quicker, but we cannot change the KSP at a certain temperature. The increasing the amount of reactants does not cause it to shift to the right because there's no more room for any more salt to be dissolved. Also, the size of the particles don't play a major impact either. So,
Can you do a supersaturated stuff?
yes.
Isn't that done by heating it up a lot and then cooling down slowly?
Yeah. So that's But even then, like, it's easy to trip out. So naturally or normally, yeah, you can create a supersaturated solution, but you'd have to do it under extreme conditions. So, yeah.
Really, really cool to watch. You know, put the stick in a couple of water and goes into sugar in 3 seconds.
Yeah. All right, so here's something that I want to make sure that we understand. Okay, so we have solubility product and solubility. Solubility product is referred to as KSP. Right? I'm going to refer to solubility as S. And let me kind of relate S to something you're familiar with. From the other chapters, S is X. What I mean by this is S or X is our equilibrium position. Do you remember how we could have a variety of equilibrium positions but only one equilibrium product? Right? The ratio always stays the same, but the numbers in the ratio can change. That make sense? Because if I add a common ion, it's going to change the numbers in my ratio, but the ratio will still be the same in the end. Okay? So we'll do a problem seeing exactly what this looks like. But I just want to make sure that we're clear that when I'm talking about solubility product, I'm talking about the constant. And when I just refer to solubility, I'm talking about usually concentration. Okay? Stuff is the biggest joke of all time.
You're right.
Yeah, stuff doesn't.
Why, because it kills good germs, or?
It doesn't even kill the bad germs.
Nice, rub it in.
I mean, biology, they did that, put bacteria on the hand, and then they put Germ-X on it and rubbed it in, and it killed
You're not
like...
supposed to rub in you're supposed to let it, rub it on and let it dry. So, I don't know.
Oh, so like you might not do like a coating?
Yeah, you just like put it on your hands and then kind of let it dry.
Anyways, I don't know why I got off on that. Alright, let's do this problem. So, if you remember, the dissolving process was a little bit tricky because we had to remember that things broke up into more particles. So, for example, if I have CaF2 and this breaks up into Ca2 plus and 2F minus, if I know the molarity of this is 2 molar, or I have 2 moles of it, how many moles of calcium do I have? 2. And how many moles of fluorine do I have? 4. That was something that can easily cause some problems. Okay? So if we're doing this particular problem, we have copper 1 bromide. Well, that's nice because it's a simple 1-to-1 ratio. CuBr, right? 1 plus, 1 minus. Quick refresher. Yeah? Okay, that's going to break up into copper 1 plus and Br 1 minus. Okay? And we could write our KSP expression. This first one's pretty simple. Look like that. So we know this is going to completely dissociate, correct? Yeah. So isn't my solubility of this 2.0 times 10 to the negative 4th? Well, what's the concentrations of these then? The same. Usually I will say that this is S, S, and S because all of them are a 1-to-1 ratio. And so I can just say KSP is S squared. because is this ever going to be in the equilibrium expression? Okay, so this is the solubility of this guy. So it really ends up just being the square root of your KSP. Or sorry, not your KSP, the square root of your, what am I solving for?
2 times 10 to the
Wow.
squared, right?
I'm solving for KSP. Yeah.
I was thinking I saw him for the other one there for a second.
There you go. So your solubility product will be, this one's an easy one, so
We're not in the negative eight.
that wasn't too hard.
Next one.
A little bit, but I'll show you kind of a shortcut that should help you quickly be able to do this. Okay, any questions on this before I move on? All we're doing, everything was a nice 1-to-1 ratio, so I knew that these were the exact same, plugged them in, found your KSP. The next one's not a 1-to-1 ratio, so I'll show you how you would do a process like that. I always start by writing the equation. So we have Bi2S3. That will break down into what? 2Bi, what's the charge? What? 3 plus, good job, Annie. Plus? Yep, good job. Now, I'm going to kind of show you 2 methods of doing this. Okay? When you're doing your equilibrium expression, so KSP, quick refresher that the coefficients become exponents, yeah? There's multiple ways you could do this. Okay? I know the solubility of this. It's 1 times 10 to the negative 15. Correct? Okay? And I know that this is going to break up into twice the particles and 3 times the particles, so I could take this, times it by 2, plug it in. Take this, times it by 3, plug it in. Okay, but I'm going to show you one other method, which will, if you can figure out it actually speeds things up a little bit. So this, since it has a 1, that's S. We'll say this is 2S. We'll say this is 3S. It's how they relate to each other from a mole standpoint. Right, then I'm going to plug that in here. So it's really 2S squared, 3S cubed.
It's something like this.
Yep, we did. When you solve for that, you got 4s to the second times 9s to the third. When you simplify all that, you should get 27s to the fifth. Well, we know s, don't we? Everybody see what I just did? I'm essentially... Go. Yep.
No, but 3 to the third is 27.
Yeah,
Yep.
it's 27 times.
That's why you guys are here. Told you don't write in pencil. It's 108, isn't it? I should just look at my notes. Did I do that right now? Sorry. Okay, and since we know what S is, It's tiny.
1.08 times 10 to the negative 73rd.
Yep. Now, could I have taken this number times 2, plugged in here, take this number times 3, plugged in here, and solved and got the exact same answer?
Yeah.
Yes. So whatever you prefer, if you would just rather write the equilibrium expression, eventually you're going to get to a point where you're going to see that it's a 2 to 3 ratio, and you'll go KSP equals 2S, I have to square it, and then 3S, I have to cube it, and then you'll just solve that and plug in either your S or your KSP and solve for the other variable. Does that make sense? Because I could give you KSP and ask you to solve for the solubility. Does that make sense, everyone? Okay, that's what the next problem's asking you to do. So, whatever you prefer, doesn't matter on a test. If you want to do, just take and multiply by 2, plug in, multiply by 3, plug in, and solve that way. Or if you want to simplify it all first and then plug in either S or KSP and finish that way, it does not matter to me. Just giving you 2 methods. You figure out what works best for you. So then this last one, notice they give us the KSP and they ask us to find the solubility. Okay, so that's a polyatomic ion. I know that because it has parentheses around it.
Which indicates that IO3 is probably covalent.
Yeah.
Okay.
I mean,
I know it is.
It's a polyatomic, yeah.
Right, I know it is.
So that makes sense from an equation standpoint.
Yeah.
Now, me, because I am pretty fluent right now with the ability to just plug in S's, let me just show you kind of quick way here. KSP equals S, since it's only 1, 2S squared. Everybody see that? Now the only problem with doing the short way is don't want to forget the process. What we're doing is we know that this is going to break up into twice as many moles, and so that's why we have 2 times the S. Okay? And this comes from the fact that the equilibrium expression needs to be squared because of the coefficient. Okay, so let's not forget the process, but this is the quick way to do it. So then you have KSP equals 4S to the 3rd. And we want S, so plug in KSP and solve for S. You guys know how to, you can figure that out on your own? Now here's where I'm hoping you can make a connection here. What are the units for S? What? It's backwards. What did you say the units were?
That's multiple.
Yeah. So remember how we said S is your equilibrium position or your concentration? Okay? So what this essentially tells us is how much of this guy will dissolve at equilibrium. So you should get, I think, 3.3 times 10 to the negative 3 moles per liter. So this is my saturation number. How much of this will dissolve? Once it gets to that amount dissolved, we're at equilibrium and we have no more net change. Does that make sense? It's really important to understand what S is referring to. It is the solubility or the max amount that can be dissolved of a particular salt. Okay, we're done. Questions on this? So be careful, because sometimes they might ask you to solve for solubility or the concentration, max amount dissolved, or they might ask you for the solubility product. Okay? And you're going to find that when it's a 2 to 3 ratio, it's always 108 S to the 5th. When it's a 2 to 1 ratio, it's always 4s to the 3rd. When it's a, there isn't any other ratios probably, is there? 1 to 2 to 2 to 3. Maybe 3 to 4, but I doubt it. So really it'll either be 1 to 1, 1 to 2, or 2 to 3. Either it'll be s squared, 4s to the 3rd, or 108 s to the 5th. Because it won't be 2 to 2, right? 2 to 2 just rounds down to 1 to 1, right?
Okay, can you, why is it 4s? Because it's 2 squared.
So so
Yeah.
the 2 has to
Got
get,
it.
cube that and make that
Yes, got
square.
it, great, yep.
That's a cube squared.
Yeah. I was thinking of it as the 2 being inside parentheses as 2s.
So it's just
2
2s
times s
squared.
squared.
Yeah, be careful,
It's
because
2s squared.
this has to go distribute to both.
Okay, yeah, it's 2s squared, not 2 times s squared.
Yes.
Got it.
So think of it back, if I were just to write the equilibrium expression, you would have the 2 on the outside, and then you would plug 2s in, and then you have to think of it that way.
Yeah.